session. Today we are delighted to have two of our distinguished colleagues here to present to us, to help teach this tutorial on TidyModels. So we have with us Professor Samara Kiihl. She's an assistant professor in the Department of Statistics at AIMM, Unica, and she holds a PhD in biostatistics from Johns Hopkins University School of Public Health, and her research focuses on applying advanced statistical methods to biological data. Let's welcome her. And we have Professor Tatiana. She's also an assistant professor in the Department of Statistics at AIMM, with a PhD in statistics from Pennsylvania State University. Her research focuses on statistical modeling, especially mixture models and linear models applied to diverse kinds of data, as we shall see today. Thank you very much.
You're welcome. Thank you for the introduction. Thank you all for being here. So today, Samara and I will give you a tutorial. I'm not an expert in malaria modeling or epidemiological modeling, but we're going to show you a tool that you can model these things and give us, a good model. So this is an introduction. A fun fact about me and Samara: we started as professors here exactly on the same day. It's been 11 years now, right, Samara? So, what we'll cover in this tutorial. First, we're going to discuss about statistical modeling and machine learning, because they're two different areas, but they can have a common ground, which is, for example, the area that we call statistical learning. So many things, sometimes what we say is more like in the classical statistics, the way we name things, or in the machine learning area. So we're going to give you an overview of the Tidyverse universe, because that's where TidyModels is based on. And then we'll talk about TidyModels, highlighting its applicability and benefits over other approaches in R. So why should we, put some time on learning TidyModels? And you'll see that makes for modeling. I always say that to model things, you cannot be lazy, because you have to explore lots of different things, like type of models, parameters that you have to estimate, the hyperparameters. So there are a whole bunch of things that you need to investigate. And with TidyModels, that task is much easier. And also because it has like an integrated interface. So we're going to talk about fundamentals and applications of TidyModels, exploration of the main package. Since TidyModels, it's not a package itself, it doesn't have functions in it, but it's a set of packages for modeling. And then Samara will show you some applications to a practical example about malaria data. Here we're saying predictive regression models, but here we're talking about classification models, okay? And then we'll have some space to discuss, but also if you have any questions during like my talk and Samara's talk, feel free to raise your hands and we'll discuss. Okay? So who is this tutorial for? It's for you guys. Okay? But if you have basic knowledge in R and RStudio, since TidyModels is a set of packages within the R ecosystem, be familiar with the Tidyverse structure, so like using pipe and functions like dplyr, tidyr, ggplot, how to read data. So it's more in this scope, okay? And statistical modeling, machine learning, you don't need to be an expert, as me, in modeling, but it's desirable that you can understand some concepts, like when we talk about regression, classification, cross-validation, some metrics, that you have some idea of what we're talking about, okay? So I'll start asking you this. In your opinion, what's the relationship between statistical modeling and machine learning? Or is there a difference?
Well, I'm not a statistician, or I don't know much about it, but I think that the machine learning uses statistical modeling to predict something. I know if I'm right or
No, that's in the right direction. Any thoughts? No. Samara? You should. Well, okay.
Yeah, but statistical modeling is more concerned with interpretation of the data, while machine learning is more concerned with accuracy, model prediction, accuracy of the models, and so many other differences. That's one.
Yeah, that's the main, at least what I see, the main difference. Statistical modeling focuses on understanding the underlying relationship between variables. So, if you think about interpretability and inference, like you want to see which predictors have a significant effect on the response variable, right? On the response variable. And often you begin with a predefined model based on theoretical knowledge or assumption about the data. And you use the whole data to fit that model. In machine learning, it's more about predictive modeling. So sometimes you don't care if you can interpret your predictor or your features, but you want to have a good accuracy of your model. So it's more about that. Involves more flexible, data-driven approach, in the emphasis is on algorithms that can learn patterns from data without strong assumptions about the model's form. But there is something that is called statistical learning, which I think it's a combination of these two areas. Like you can have a good predictive modeling, but you also care about like individual effect of your variables and also the inference of that and the interpretation of that model. Especially in, I think, like medical research. Sometimes you want to know like how a good diet can change your response and things like that, okay? And then, so machine learning, in the area of machine learning, we have two classical type of models. So you have supervised machine learning algorithms and unsupervised, okay? The supervised part, which is the ones we are going to work with, is supervised because you have a response variables, and most of the time you wanted to like make a classification. In our example, like you wanted to check if you want to predict the severity of malaria based on some features. So then you have a response variable. In the unsupervised, it's more like you have a set of features and variables, and you want to find some similarity, and you want to identify patterns in that data. So not necessarily classifying anything, just to see if you have a common structure, okay? So I used to say it's the difference between, like if you teach a child, you show like a basket of fruits, and you take an orange and say, this is an orange, and you say, this is a banana, this is an apple, and then you give new fruits, and this child is going to classify, oh, this is an apple, this is a banana, so that's supervised, right? But if I just give, she never heard about fruits, I give her a basket, she's going to classify like the red fruits, the yellow fruits, the round fruits, so it's going to find a pattern that you can put these fruits together. That's unsupervised, okay? And we're going to work here, and the difference between classification models and regression models, when we say regression in machine learning, is not only linear regression models or linear models. is when your response variable is like a continuous variable, something quantitative. Okay, and in the classification is when your response variable is a categorical variable. Like when I say the severity of malaria, the severity of some disease, or classifying the type of fruit that I see. If I get some images, pictures, and I want to classify the type of animal is in it. Okay, that's a classification problems. Here it says divide the socks by color. See, divide the ties by the length of the tie. So it's based on the type of your response variable. Okay? And then why learn TidyModels? So TidyModels, you are just started. If you're just starting today, you've never seen this before, or if you have years of experience in modeling, TidyModels offers a consistent and flexible framework for your work. Anybody here has worked with TidyModels before or no? No? You?
So I forget all the time.
Oh, that's the thing. You don't know by heart. You just have to learn. The idea is, yeah.
There you go.
Yeah. Even for us, like trying to put this tutorial together, there are so many things. So the idea here is to show you what is the structure of a tidy model and its components, and then how you can change from one model to another. The idea is to be very intuitive. Like if I want to fit a random forest or a classification tree, so it's all have like the same. It's basically the same code. You only change few things. Okay. So just to start with, we're going to talk about the data analysis process. So you have to import your data. This is the tidyverse part, where you read your data, you tidy your data, so you clean up everything, then you transform whatever is necessary. You do the descriptive statistics and exploratory analysis, so you visualize your data, then you come to the modeling part. The modeling part, sometimes you see things that you have to go back to transform your data, visualize again, and then come back to. And that part of the modeling is that what we're going to do with TidyModels, okay? And then you share your results, then using Markdown and Shiny. We're not going to get to this part. So the source here, there are lots of, we have lots of materials here that we indicate in this tutorial that you guys can read later. So just going back to the tidyverse, just to remember, the tidyverse is a collection of packages that share a common design philosophy and work well together. So always these packages, like basically they started with ggplot, and then they came with all the packages to manipulate and clean data, deploy, and then there are the forecasts, which works with date and time, and then strings, reader to read the data, and then things like that. It was developed to make data manipulation, exploration, and visualization more consistent and intuitive. Okay? And then to install is just to install the tidyverse.
So if I load the library, can I load difficult?
Yeah, I had that question yesterday with my students because they're like, no, I'm just gonna use reader. So just load the tidyverse, because then it loads all the packages like reader, deployer, ggplot, it's all there. So and it's gonna be the same with the TidyModels. So you can load the libraries by itself, one by one, but you just load tidyverse and TidyModels. That's it.
And you have everything.
Yeah. So these are the packages that the core packages of tidyverse. So it's all there once you say library tidyverse. Okay. So ggplot is for visualization, deployer data manipulation, tidyr data organization, reader data importation, per is functional programming, like to replace things like apply, you guys have, or for in the vintage R. Yeah. Table is just a modern data frame. which is to visualize, it shows it very nice on your screen. Strings, it dealt with stringer, and then vectors with forecats. Oh, I said, it's the lubricate, it's not here. Lubricate is date and time, and forecats is for vectors. Okay? And then going to the TidyModels, which is basically the same idea. It's a collection of packages for statistical modeling and machine learning using the principles of tidyverse. So usually with these packages, like the input is a data frame or a table, and then the output is a table. So it makes it easier to go from like one package to another and to work with these things. So then you install TidyModels package. So, but here, what is important to know? It's important to clarify that the set of packages that make up TidyModels only encompasses existing statistical techniques. So what you know, like to fit a regression model, the LM function. So that's what it's going to use. So it didn't create new functions, or it's just a collection of functions that's already in R. The TidyModel concept aims to make all tasks related to model fitting much easier, more intuitive, and more understandable. So when you read a code, have you tried to get someone else's code? To say, okay, I'm gonna, so if you have a student or if you're sharing with a colleague, yeah, if you like this tidy, then, but working with TidyModel, it's easier to understand, like step by step, what that code is doing, because it's more readable and intuitive. Okay. So what we're gonna do in the modeling steps, we're gonna have. So we want to. That's the part training our model or fitting our model. When I say training, is because of machine learning area, but for statisticians, we fit a model. So it's this part here. But before training your model, some models requires that you have to transform the predictors, you have to like scale or normalize your predictors, you have to convert numerical predictors or categorical predictors to vectors and vice versa. And that part is all done by the pre-processing part, okay? Also, in machine learning, sometimes, not sometimes, all the time, you split your data into sets. So there is this part of the data where you're going to train your model, you're going to find your parameters, and then you're going to evaluate and have a final model and a final accuracy in the test data. So that part, we split our data, and then this package here also is used for different types of resampling, like cross-validation. It's all done by this package called RSample. The recipes, it's the pre-processing, what I was just saying, like if you have to transform anything, if you want to exclude variables that have, like the variance of that variable is 0, so it doesn't contribute to explain your response variable, so you can take that out of your model. If you want variables that are highly correlated, you could do this here. So you say, oh, can we do this before? No, we're going to do as part of your, what we're going to call workflow. So the pre-processing and then the modeling part. And then the parsnip is a common interface for model creation. That's where we're going to define our model to then fit it. And then the yardstick, this part is where we validate our model. So there are metrics to measure model performance, to validate and choose like the best model and then the final model as well. Okay? So the core packages, I cited some packages here, but it's not only these packages that composes TidyModels, but the first one, so the TidyModels itself is a package, but it's a collection of all those. And then, as I said, our sample, it's infrastructure for resampling. So you're going to see that here, to do a cross-validation, it's very easy. Parsnip is a tidy, unified interface to create models. Recipes, general data preprocessor with a modern interface as well. Then workflows that is going to combine the pre-processing part and the model part into a single object. And then you have the tune packaging, which is to optimize your model finding hyperparameters. The heuristic, the tools, so any metrics that you want to compute, like the mean square error or the accuracy, things like that are here in this package. And dials, tools to create and manage values of tuning parameters, so these things work together. And Broom is just, to clean up the messy outputs into tidy data frames. So if you have fit like a linear model with LM, there's a type of output. And then if you fit like a GLM, I don't know, logistic regression, you have a different type of output. If you do a random forest, it's a different type of output. So these things is kind of takes each of these outputs and try to make they look alike, So that's the idea. And depending on your goal or the type of model that you train, only some functions from some packages will be used. So it's not that you use this all the time. If it's a simpler task, maybe one and another. Sometimes you don't have to pre-process anything, so it's just simple. Okay? So then going to the malaria, since this is the workshop about, I'm going to talk about these data sets that we are going to use throughout our tutorial. Okay? So malaria is a life-threatening disease, usually transmitted through the bite of infected female mosquitoes. Okay? It has this life cycle here. And we're working with this data set related to malaria symptoms, available from this paper, Malaria Patients in Nigeria. Okay? This data here, it's about malaria symptoms reported over a period of 4 weeks by 337 patients attended to at this medical center in Nigeria. And for some code and for the data and the code used in this tutorial, Samara has prepared a nice vignette where everything that we've done here, she put it together in a nice document, in an HTML document. So just go there, and if you have questions, you ask Samara. Just kidding. So here is, to look into our data, what we have. So reading our data, the CSV file from this website here that you can read straight to R. And we're going to take a look. So we have 18 variables. One of them is the response variable, which is this last one, which is the severity of malaria. And everything else, you can see here, everything else is binary. So it's a yes or no response. And then, but it's already in a dummy format. Yeah. So this is one thing you need to check, because if this was like yes and no, so it would be a factor, then you would have to transform this to a dummy variable. But this is already done for us. And then the age of patients, it's from 3 to
77.
Yeah, I guess it's from 3 to 7. That's the.
I think it's 77.
That's the owner of the data.
Yeah.
That's the boss.
Yes.
Yes. Yeah. So age, and then lots of things that was observed. So the sex, fever, cold, fatigue, headache, vomiting, diarrhea, and so on. And then I was curious about this one. Coca-Cola urine. What's that?
Coca-Cola
urine.
That is like reverse problems. Then the color of the urine becomes dark.
Oh,
Yes.
then it's
because
called.
of the situation of the urine.
Oh, I was thinking that they were checking. No, they were checking if there were Coca-Cola.
No, the urine looks like
Looks like
Looks Or in malaria also.
You can have low when you have severe malaria.
Right. Okay. And then the last one, the severity, if it is severe or not. So then here we're just renaming these for severity, okay, to make it simpler. So here I have all the names of that we're going to work with. So we have 337, see, you can see here, 337 observations and 18 columns. So one of them is our response variable, which is binary, and then we have 17 total that it's all binary predictors except for age, which is numerical variable. Okay? So just to look into like nicer, like an Excel table. I put some columns here, it's not all of them, and then the severity here, okay? The response variable is severity, which is binary, so we have to transform this as a vector, and we need to set the event, which is if the disease is severe, as the reference level, okay? So that's what we are doing here. And then the dynamic will be, we're going to split our data into training and testing sets. We're going to choose a specific model. Actually, we're going to pick like 3. Was that 3 somewhere? Logistic regression, decision tree, and random forest. So we're going to choose and specify a model. Then we're going to pre-process. I said quantitative much easier than I say pre-processing. Anyway, no, I pass. And then we're going to go to evaluate our model's performances through some metrics, and then we're going to use cross-validation for model validation, and then we're going to use this tool to search for hyperparameters. Okay, Samara will show you these parts. See, we use our sample in the beginning, and then parsnip, recipes, yardstick, and then we go back to our sample to do the cross-validation. So it depends, that's what I said, depends on your test, you go back and forth using these packages, okay? So the first thing is to split your data. So in machine learning, usually we split the data into training and test sets. The training set is used to estimate model parameters, and then the test set is used to find an independent assessment of model performance. Usually we say like, you put this test set in a safe, and then you're going to work until you have your final model with the training set. You can also have the validation set that Samara is going to talk about, but for now it's just we're going to take a random sample of our original data and separate between training and testing, okay? And then, that's what I said, test data is precious. You put them in a safe, never use test sets to train your model. Why is that? Because modeling is very optimistic related to your data. So it's going to find anything, if we do like ordinary least squares, the technique is to find, to minimize the error according to that data you are seeing. But that's why it should be a good model for that data. But we want to know if that model generalizes well if I have new data. So that's why you keep this testing data away, and then you're going to check the performance of your model in the test set. Okay? To do that, we're going to use the R sample. So see, I wrote here the TidyModels, which basically what I'm using is this function, initial split, from the R sample package. So we're going to split our function. So I just say what is the data set that I'm using and the proportion that I want in each set. So I say proportion 80%. Tatiana, you take care to have like similar, something like similar spoiler distribution or pattern in the test and the training, because I think that's important. That's our next slide. Okay. That's it. Like the original data, 80%, see, I have this, the total 337, 80% is gonna go to the training set, and 20% to the testing set. The default here is 75, but that's a question, like what we use for the training set and leave for the test set, okay? But check that this output, this object here, it's not splitting your data. It's just saying like the indexes that goes into each set, okay? And then to extract your data, then you use the functions training and testing, okay? From that initial split. And then you're gonna take training, testing, and that's one question. What proportion of the data should I set aside for the test set, okay? And you need to think about these two things. Okay, if you want to spend, what we want good, the more data I have, the more accurate are the estimate of my parameters, right? But then I don't leave much to access the predicted performance of my test. And if I spend too much data on testing, then I don't have a good estimate of the model. You never win. That's the thing. So you have to find, usually they say 75, 25, and also depends on how many observations we have. Like here we only have 337, but sometimes you have thousands of data, then you are fine. So that's Mariana's question. Splitting the data that way, so just taking, for you guys who took sampling classes, so if you split your data just a single random sample, see, we are interested in predicting malaria severity. If we take a single random sample, it could happen that none of them will be in the test set, for example, right? So then that's the risk you take when you do a simple random sample. Like here, what we did before was a simple random sample, like this one. So the original data, see, I have 34% of severe cases, and then in the training set, 35, and then 30 to our testing set. Well, it's not that different, but just to show you that it should be more similar. And to make sure, then we are going to do a stratified sample, okay? Because then we divide into the categories that we have in our response variable, and then we make sure that we have samples from each one, keeping the same proportion in each set, okay? So then that's what we do. We say the proportion, and then what is the variable that defines your administrator, okay? Which is, in this case, is severity. So now, see, we have all the same, about 34-35% of severe cases, and then because the testing set, it should be representative of your whole data, the same as the training set. Okay. So certification ensures that the test set maintains a distribution close to that of the training data, and you have to think if your response variable is categorical or continuous. If it is categorical, it's just a stratified sample that I told you about. And if it is continuous, then what it does, it splits your data into quartiles, and then it makes sure the quartiles match in the training set and the test sets.
So what if you need to also stratify the gender?
Variance.
Severity index is different for each gender.
Yeah.
So you want to stratify by severity and gender.
You could.
You just
Yeah. So it depends on your problem. Here, usually, you have to include the response variable, which is the one you are trying to predict. But if there is a reason to include the covariates, then you can put in there, which the ones you define. Okay, so let's go to part 2, where we're going to talk about the structure of TidyModels. Okay, So let's start with another question. If you think about linear models, how would you fit a linear model in R? Ellen? Where's my regression student?
That's it.
LM is yeah. That's how we can remember, right? But there are lots of, it depends on, I forgive you guys because we only use LM. But if you go to another class, which is generalized linear models, that you use yeah, GLM net for regression with regularization, GLS with generalized least squares, MER for linear models with mixed models, and so on. STEM for Bayesian regression. So see, the challenge in R when using different functions, so even if they do the same thing, is that they can have different interface and arguments. So I'm going to show you some, for example, if we want to fit a random forest, okay? So I choose, okay, I'm going to use the package random forest with the function random forest. So in random forest, you have to define the number of trees that you are growing in your forest. So in this function here, the argument is n tree. If I use ranger, which is another package to do the same thing, then the argument calls num.trees, okay? And then in Sparks, it's num_trees. So see, it's the same thing, but they don't agree. We understand that it's the same, but it's all different. So you have to go to the function and check the arguments and then see how you can name them. And if you want to change, okay, I don't want to use this one, let me check this one.
Go back, change everything.
You have to go back and change everything. So then, if you use parsnip, what do you want to fit? You want to fit a random forest. Here. Number of trees, it's called trees, okay? 2,000. That's it. What this package is going to do, see, this is not a function. It's like a phone. If we're talking different languages, it's a translator. Okay? So then I say, I'm going to use this with 2,000 trees. And then I define if my model, my engine, what I'm going to use to fit this model is from Sparkly R, Ranger, or Random Forest, okay? So it makes the translation between trees and the actual names of the arguments of the implementations. Let me show you here. Don't worry about these steps which we are going to see. That's the structure of the modeling part in TidyModels, okay? So we need to define the model that you want to fit. So this is a random forest with 2,000 trees. We're going to use the package random forest, and it's a classification problem, okay? And then I have to translate. See, I do this, and it translates to me. So it goes random forest, that's the package, that's the function. So I have X, I need Y, and then n tree is 2,000. See? If I change here to, instead of random forest, I put ranger, it's gonna get the corresponding argument. So it makes the translation to you. So it's much easier. All you need to remember is the type of model that you want to fit, the engine, so which function you want to use, which package you want to use to fit your model, and then the mode. Some
also, like, it has some defaults. If you don't specify the engine, it has a default.
Yeah, like
then
here,
you need to check what they are. Right?
Yeah, random forest here, I put the engine random forest because the default is ranger.
Yeah.
Like if I fit linear regression, the default is LM. So there are some things already there for you.
These trees constant, or you just have to trees 2,000, see a constant value, or you know.
You can set this.
Oh, here I'm setting to 2,000. But Samara is going to teach you how to do it.
If you don't choose trees 2,000, the default is 500.
Okay.
So it has defaults for everything. If you just say, I want this model.
Yeah, but you can also tune that parameter. It could be a tuning parameter of your model. But that part is fixed. It's just to show you how it translates to you. Then, what is parsing in TidyModel? It's just a standardized interface for fitting models to make predictions. That's it. Okay? So, that's what you need to specify a model in TidyModels. That's what you need, the steps. You choose a model, you specify an engine, and you set the mode. Some models, like linear regression, all you can do is, the mode here is always regression, so you don't need to put anything. But like random forest or decision tree, it could be for classification or regression problems. Then you have to set the mode that you want. Okay? And then the terminology. What is a model? Differentiates the structural form of your model. So if it is a linear regression, if it is a random forest, a logistic regression, and so on. So you're just saying what you're gonna fit. Okay? And then the engine, it's the mechanism or the computational method indicates how the model can be fitted. Okay? So there usually are packages like LM, GLM, random forest, but they can also be methods outside R, like scan, spark, and all. And the mode is the mode that will be used. So it is for classification, it is for regression, but there are other things like sensor regression and so on. So when choosing a model, we are just defining the functional form that will be used. Okay, so here, we're gonna fit first a logistic regression. So that's it. And also the names, it's supposed to be very intuitive. Okay, like rainforest, logistic array. Try to make the name not so long, but also you understand what's to. And never use, even Tidyverse or TidyModels never uses dot in the name of the variables. Yeah, I always say that if you see a dot, like for reading, yesterday my students, they are reading a data set, they put read dot table, that's our vintage. Read underscore delete.
Yeah, because they use the dot for some variables, and it's special variables.
Special variables, exactly. So the names are always with this underscore.
Yeah.
So here, see, I didn't put anything. I just said logistic regression, and the default engine is GLM. Okay, and also the default is for classification because it understands logistic regression. Always have it's a categorical variable as the response. So you don't have the option to change the mode. So after the form is specified, we need to think of a method. Here is already GLM, but it could be other things like, so see the arguments here, so the mode, it has the default. The default here is GLM if I have a penalty, if it is a mixture. So then if I change the engine, so see as set engine to GLM net, now I changed how it's going to be fitted. Okay? That's all. And for a list of models available, you just check this. It's not all in this table, but it's going to be a table like this one. Like for logistic regression, see all the types of engines, it's always classification in this case. But you have different types of engine. If you want to do like via GLM, GLMnet, Keras, and so on. Okay? Like decision tree, another one. If my model is a decision tree, then I can use for classification or for regression. Then I need to set the mode and also the engine. If I use part, if I use Spark, and then you need to set the engine as well. So after specifying your model, before proceeding to fit and train your model, we have to do the processing part. Okay? Some models require predictors to have certain characteristics or formats. Some variables require some transformation. And to do this in TidyModels, it uses what's called a recipe. Okay? So the type of processing required depends on the type of model to be fitted. So you need to think, it's not always the same. Like some models they use, if they use some distance measures, they must have all of the predictors, like the continuous predictors on the same scale, okay? Because, so then they calculate the distance properly. For example, if I have a model that's going to calculate the Euclidean distance, and you have one variable which is your age, and another variable which is your annual salary. So the annual salary is another scale, so it's going to dominate your distance. So you need to put that on the same scale, so we need to normalize. But not every model requires that, okay? And we need to have our Rebecca. Our Rebecca Andrade. Because she thought, I don't know if you guys watched it, but for us in Brazil it was really funny because they were asking her, what was your thinking before like jumping? She's like, oh, I was just thinking about the recipes that I see. I see lots of recipes on the internet. I said, do you cook? No, I don't. But I save them, but I never make them. So since we're talking about recipes, we needed to bring. This was actually the day, right, Samara? We had to present this tutorial. And it was the day that she won the gold medal. It was Samara and I were driving to the place. And I was like, oh, let's go Brazil. Sorry, Nigeria, but she's the best. So what is a recipe? Just for you guys to remember. It's a description of the steps to be applied to the data set in order to prepare it for analysis. So the recipe, the first argument of the recipe usually is the formula that you're going to use. And the formula is to tell your model which one is the response variable and what are the features, the predictors, okay? And then the steps. I'm going to show you what these steps could be. So let's go. Like this one, a simple recipe is just defined in the malaria trained data. I say severity and then everything else in my data set is going to be predictors, okay? So then you see here the role of each variable. I only put some so you guys can see, but we don't have 9, we have 17 here. So severity is the outcome and then everything else is are the predictors. Yeah. And then the recipe, see, you specify your variables, the roles of your variables, and then you do the steps, okay? So like we can scale, we can center, normalize, we can transform, create dummy variables, and there are lots of things to do. And then you have to prepare your recipe and you have to bake your recipe, okay? That's what we, these artworks, they're so cute, aren't they? Yeah, I know. So here are some that I already said some of them, like dummy creates a variable coding for categorical predictors. ZV removes the predictors with a single value, like in that one. If the severity, I'm checking the severity of malaria. If everyone has fever doesn't discriminate if it is severe or not. So I can exclude that predictor, okay? So that's what this part do. Input, you can input some missing values. You can choose if you have, we know that like in linear regression you have multicollinearity problems. So if you have predictors that are highly correlated, you can say, oh, if the correlation is above 0.9, you can exclude one of them because they give you the same information about the response. Okay? Normalization, so to center and scale. Transform if you want to apply some transformation to the data. And then here, say, in this side here, for recipes, there is a whole cookbook where you can get the recipes you need.
Excuse me.
And then, sorry,
I don't want you to do the feature selection.
sorry?
The feature selection. Feature selection.
Selection.
Oh, feature selection.
Feature selection, TidyModels, they recommend you to do like using like a lasso kind of regularization.
It's not at the point where you
No.
want to fit this.
No. The recipe is more before you feed the data.
Like a pre-processing.
Yeah. It's before you have your data ready. It's gonna get your data ready to be to feed your process.
Does it come before pre-processing?
No, this is for
The recipe is the pre-processing part.
You're just saying, I want you to pre-process the data this way, and then I give the instruction like convert to dummy, they correlate,
I'll show you.
exclude
So here's the recipe. You say the formula, and then I do all nominal predictors. You create a dummy variable,
You
and
can,
then all numeric predictor. You check if they have zero variance. If they do, it's going to be excluded from your model. Okay? So that's all the steps that you define what you're going to do with
and
it.
you can choose many steps as you need.
Yeah.
So it is after this you have the feature selection?
No.
For
The
example,
feature selection is gonna be after that,
after feeding your model.
after feeding the model.
After this?
Yeah.
This is the first part.
Yeah.
Okay.
Just getting data set clean and ready.
And ready.
Yeah.
So this is more like a data cleaning.
Yeah, yeah. It's a big process.
But it's in the context of modeling already. Because you can clean your data and leave your data there, but
And one single code can do all these steps.
yes. And one interesting thing is it depends on the method you are feeding. It's require different preprocessing, like logistic regression. You have
Different ingredients.
Yeah, logistic regression, you need the dummy variables, you can use the zero variance, you can do some imputation, but you don't need to normalize, for example. Or, I guess the cross is no, and then the dot here is maybe. You could transform some
And if
variable.
we do imputation, maybe to take into account listing values, do you account for it in the model that you did something like that? Or just have to skip it?
Just gonna impute.
Yeah, you can.
But it is documented that you did.
Yeah. And there are different methods to do the imputation. Okay? So if you do like the nearest neighbor, you need to normalize your data because that's one algorithm that you use like distance. Then you need to normalize all of your data. So those are the Poisson regression. See, random forest. Random forest, you basically don't need to do anything except if you have.
I think what is important to say, the good thing about the recipe is that later on in machine learning, we end up having like a cross-validation, they're going to split the data many times and refit things. So
Yes.
it's like a whole ordeal. And then once you have this recipe, it knows exactly what to do in each fold, in each subset of the data. It says, okay, subtract that mean, which is that mean? You're not going to recalculate, you're just going to use from the trained data. And it's very clean way to work. It's easy.
Yeah, because that's the thing. Sometimes, like if you have to normalize your data, you're gonna normalize your training data. You have to compute like the mean and the standard deviation of each column. And then you need to apply that to your test set, okay? So you need to save those parameters. That's why we say the recipes are estimated.
Yeah, we are not supposed to compute the mean again in the test.
No,
That's
you don't
how
normalize
this is
yeah.
useful.
And if you do like cross-validation, it knows which parameters you're going to apply to each fold that you're going to give out and then you're going to work with, okay? So recipes, that's what we say. Oh, and the order of the steps matters, okay? Whenever you see pipes, it's a nice way to read these codes because it's like, okay, this is your formula, then you do this, then you have something resulting for this. And then you're going to do that. So if you transform, if you create your dummy variable, so you had yes and no, then you create your dummy variable, which is 0, 1, and you normalize it.
No.
It's going to normalize it, okay?
It's going to normalize the 0, 1, and that's
As I
how
say,
much
like this is a tool, but you have to know which step you should do first. Yeah. So then here I create like the dummy. Here we don't have to create the dummy variables because it's already, we don't have nominal predictors there. But just to show you. And then we also don't have anything with the zero variance. But just to show you these things. And then recipes are estimated. So like dummy variable, you need to check how many levels of the categorical variable you have so you can create. If you have 3 categories, you need 2 variables and so on. And then you estimate these parameters from a recipe that's from an initial set that's going to be applied to other sets. Okay? That's why it's interesting. Like here, a more complex. Age is the only continuous predictor that we have. So just to show you, we could define like a second degree polynomial to fit here. So we already create like the x squared, and they are orthogonal. So then once I have my recipe, everything I should do, like I say, you need flour, sugar, anything else. Then what do? You prepare your recipe and then you bake your recipe. But we're not going to apply these steps because this is going to be done when we include this recipe in our workflow that we're going to talk soon. And then when we do fit our model, it applies the recipe and then fits our model. So it's all together in this object that we call workflow. So see, if I do this in my data set, for the training data, that's what I get, okay? And this I showed the last 2 because it creates like the age, the first degree polynomial and then the second degree, okay? And then everything else is just zeros and ones. And then let's go to workflow. So then we saw that we need to define our model, where we choose the model, we set the engine, and then also we put the mode that we want to use our model for. And then to combine these 2 things is what we call a workflow. Workflow is just the management of the pre-processing steps and the model all together within the same object. So like a workflow, I have here my recipe and then my model here. Okay, you put this all together. And that's the thing. So considering what we said before, do you think this is a good workflow? Like principal component analysis, we use for what?
Just to reduce dimension, right?
It's kind of dimension reduction, exactly. So this is a pre-processing part. So that should be in the workflow. Okay, so PCA, it's included here. So that's what you need to think. The workflow is not just fitting your model. It's the recipe, the pre-processing, and then the model specification. Okay? And then we have your model fitted. So we workflow. We split our data, then we have our recipe, and then we have our model, like linear regression, logistic regression, and so on. They help you to organize your work, because we're going to see that we can test many combinations of recipes and models all at once. So that's why it's nice to use this. So especially when you are working with numerous models which requires an exhaustive search. That comes back to what I said, you cannot be lazy when modeling. Okay? So here, let's use this our workflow. So we specify our model like the logistic regression with GLM, we're going to use for classification. That's not necessary, but just to show you. And then our recipe here is going to be just the formula and then the polynomial, second degree polynomial in the age predictor. So then we define our workflow. See, here it's not doing anything. It's not fitting your model. It's just setting what is your workflow. Then we're going to get this workflow and fit the data with the training data. Okay? So now we have something that was applied, the recipe, and then we have our model. So see, in the recipe step, we have the polynomial, and this is what we are actually fitting. That's what I say. It's not a new function. It's the GLM function that you are used to with this formula, family binomial, and then the data is the data that we have here. Okay? And then, okay, I have my model fitted. How do I show you the results, like the summary in the LLM? Or something similar. The tidy function from the Bloom package summarizes the most important information from a model using the tidy concept. So here, up to here is what we have like in the summary of a regular model. But we can also, I didn't put it there, but you can also say exponentiate equals true. That is going to take the exponential of your coefficients, and I already put in there, which is something that, what they thought, okay, every time someone fits a logistic regression, what do they do? Oh, they exponentiate the coefficients, and then they check, for example, the confidence interval. So that's why it's very nice. Confidence interval, do you want it? True, I want it, it's there. You know? Do you want to exponentiate your, the estimated coefficients? Yes, so it's going to show you here. And it shows you in this nice way. Then you can see what is, I'm not going to go into detail like what is significant, and it's just to show you the structure and how it works, okay? And then, after I fit our model, I need to predict the results, right? So the predict function calculates the predicted value for a specific set. Like in the training set, and you have, it's always, the output is always a table or a data frame, right? So the TidyModels prediction guarantees that the prediction will always be a table. The column names and types are unsurprising and intuitive. So it says spread class, okay? And the number of rows in the new data and the output are the same. So we have the predict, which we were used to, but give you a vector, which is a data frame with one column of the predicted class. But if you use this function, which is augment, it's what's going to do? It's going to do the predictive classes, the probability of being in each class, which here I classify as which one that has the maximum probability. So like this one here, you can see it's not very certain that is a severe, but it's 51% and goes to class 1. And everything else, class 0, and then we have more. I just show you the first piece. So it takes your data set and it puts these columns in it, okay? It just augments the columns you have. So here, that's it.
This is good because then you have your true values and predicting the same order, because sometimes you can get mixed up.
Yeah, we're gonna see, because Samara now is gonna talk about how we compute the metrics. You have to compare like the observed and then what was predicted to compare like the
everything is in there already.
Yeah, it's all in this in a single data frame.
Qual que é o pontinho?
So we're going to talk fast with this one. I will show you
guys, you're gonna wait for lunch because we have some more.
Yeah.
But okay.
I'm so sorry. We tried to run, but
so now what we did is we chose a model, a logistic regression model, and we use our training data to fit the models, right? And then my question is, how do I know if the model is any good? What do I do now? I had the model, I had the estimates, I had the predictions. How do I know if this model is good? How can I tell? Any ideas? What I can compute, I can do, have you guys heard about confusion matrix? Right, I can compute. I can make a 2x2 tables comparing what it was actually the value, 0, 1, and what my model predicts to be. And I want to know how many times I got it right. That's one thing I can do. I can compute accuracy, I can compute other metrics, right? So I need to compute those metrics in my model. And remember, we have the augment argument and we had it predicted. Now we're gonna use that to get some metrics, right? So to compare, we can use many metrics. There's like another website where you can have more metrics you can use. Here are more or less the default metrics that it uses, okay? But there are many more, right? And then we're gonna calculate this metrics on our training, right? And then another question we have is, our concern always is how well does the model generalize, right? And then what we can do, we can compute the metrics also on the test set. Okay? So we're gonna use this function metrics from the yardstick package. First I'm gonna compute, so I have my model fitted, right? This to get the prediction and the true values that is already there. And then I use the metrics function with true. I need to indicate where is the true, which is severity outcome. And then the estimate. So I say, okay, estimate, where is the estimate? It's the breadth class variable. This is going to be always the same. This variable here, this name is always the same. The only thing we need to change is the outcome, right? If you have another model. Those are the default metrics, okay? You can choose other ones. In the vignette I left in the website, we showed how to do a custom set of metrics, right? So here's the default. You can choose many more. This is just for classification. If you're working with regression, then I have all other metrics you can use. Okay, so we evaluating the measure of the training. And then the question is this model generalizing well? What we can do then? We can compute the metrics and the test. Okay? When we compute in the training and in the test set, we just change here where we're gonna get a prediction, right? Test and training. That's the only difference. The rest is just the same, the metrics. So what we see here is that in the training layer, the accuracy was like 7%, but then in the testing, it went down to 6.2. Usually it's gonna go down. That's expected. And then the worry is, if it's going too drastic, then we were, oh, maybe my model is what we call overfitting. It's doing too well in the training data, it's not generalizing well, right? So, okay, so looking at the training data, metrics, and the testing data metrics is a way to watch out for overfitting, okay? What is the problem with doing this approach? Is there a problem with doing this approach? Is it okay? Is it wrong? Is it right? Is it okay? Remember that we discussed that in machine learning we cannot be lazy. Here, we just talked about one model that I specified that A should be a quadratic form. Very specific, right? I could have tried other models, right? And then every time, let's say I try another model, like you try a random forest, you try decision tree, and then we do this. I get the training metrics for your random forest, and then the testing, and then we compare, right? But remember, say, oh, whoever got a better accuracy in the testing wins, right? And then we can do with many models. What is the problem with that? Is there a problem with that? No? We can use the test set, right? Fair enough. Not really, because we remember the test set is precious. We're gonna have it in a safe. We're not gonna use it. So how I'm gonna decide between the three of us which model is good without using the test set? We need a trick, right? A statistical trick, right? So this is all fine if we just Logistic regression with second degree polynomial is the only thing I'm going to try. Then, okay, at this point, we can stop here. You have the testing, and that's good. But if you're going to try many different things, we're going to need something else. Because remember, the workflow, the combination of recipe and models, different workflows, we would like to test. Let's say if you try decision tree with a different preprocessing, and I do logistic regression with a different preprocessing. So all these combinations, all these workflows, we would like to test, right? So we're not going to use the test set until we already know what is the best model. So how are we going to choose the best model without using the test? Okay? We're going to use the cross-validation, okay? Let's keep here. So how we are going to do? We have our data set. In this case, it's got 337 observations, right? The whole thing, the green one. We can have two scenarios usually. One scenario is I split in two, like we did before. A better scenario is usually when you have actually three parts. We have training, validation, and testing. Let's say we have the best scenario, right? Okay, I'm going to train my logistic regression here. I'm going to compute the metrics here. My test will be here. I'm going to validate the model here. Then the random forest, train here, compute the metrics here. Decision tree, train here. Then I compare in the validation set which one got the best accuracy. Oh, it was random forest. Good. Random forest is the winner. I'm going to train, right? And do the testing here. This is my metric for the test. But I did this once. I did many times here just once. I saved it, and I use only. Okay? So, but we don't have that usually. What we do, we try to mimic this thing of having a validation. We mimic that behavior, this good scenario, using what we call cross-validation. So what are we going to do? We're going to get the training and splitting folds in parts, equal parts. How are we going to do that? Let's show you the other picture. So here's our training data. I have 30 points. I'm going to use what we call threefold cross-validation. Threefold is like, it's going to split in three parts. Each part is a different color. So I'm going to split random. So they're all mixed. One fold is the blue one, the second fold is the green, so okay? Now what I'm going to do, I'm going to mimic that validation thing that I think is good, right? I'm going to do, okay, so three folds, I'm going to do a process 3 times. Each time is 1/3 of the data, right? I'm going to use as my validation. The rest is my training. So I train here, validate, check the metrics here. The other fold is I iterate, right? And now I get the second part, isolate, train here, test here, validate here. And so now I have, for the same model, I evaluated in 3 different validation sets. So then I did the logistic regression, right? Train here, validated here. The accuracy was 62. The same logistic regression, train in a different, validate here, 64, 63. I'm going to take the average of this accuracy. It's going to be my accuracy, cross-validated accuracy. Okay?
Excuse me. Is it possible for us to divide the data sets and create different...
Sorry, say again the beginning.
Can we divide the data sets? Because within the data set we have different categories, the height,
From the covariates, you say?
Yeah, from the severity. I'm talking about the data set right now. Is it possible for us to divide the data sets Or is it possible for us to have different training model for each data set instead of combining them? Can you just
Here
go
you're gonna
back?
fit the same model every time.
Okay.
Because you wanna test how well it generalized. So I'm mimicking that validation thing. But you can do this for let's say I'm gonna change the model, I'm gonna do this process for this other model. I'm gonna do this process for the other model. I'm gonna do many times, like as many as you want.
And then you
Okay.
fit each one with a
Yeah.
cross-validation.
Yeah.
And then you compare these metrics.
The cross-validated
To
metrics
choose
from
your
each
best model.
workflow. Yeah. We're gonna show how to do together. Here I'm just showing one. Is that clear what we're gonna do? Because then the function is gonna do this on the background, but just like, okay, so this was a three-fold example. We're gonna do 5. Okay, why 5? 5. Okay, 5 could be 10, could be plus 5. Okay? Like all this discussion, like how many folds and sample size and how it behaves, like the book Statistical Learning is a good reference where they do simulation studies and explain. That's a good reference. Okay, so now we're gonna get our train data. So we're gonna get malaria train. We're gonna say, okay, do a cross-validation for me using 5 folds. So I'm gonna speak in 5. And I also want to guarantee that each fold has the same distribution of the response and everything. Okay? Now, because it's gonna do at random, every time I run this line here, it's gonna give a different split of the data to make sure everything's the same, sets it. Okay? So now, what's it gonna do? Split the data. Fold 1 has this many observations. It's usually not exactly the same, but close enough. So for fold 1, it has this many for train, this many for validation. This many for train, for fold 2. So of course these are not the same as this, right? This is all random. This together gets the whole data set. Right? This observation. So here I'm just creating indexes of my data saying, oh, this goes to fold 1, this goes to fold 2. It's not doing any calculation yet. Just saying, get your data and split in 5 folds. That's it. Yeah, it's not doing anything.
It's basically the same we did with the initial
Yeah,
split.
initial split, but just
Tells us
cross-validation.
the indexes of what goes in
Yeah.
each fold.
Yeah, it just gives the indexes. It's not doing anything. Okay, now what are we gonna do with this? What is the thing we want to do? We want to say for each fold, we want to train here, evaluate the metrics here. The next fold, I want to do the same. I want to fit the logistic regression here, evaluate the accuracy here. I'm gonna do this 5 times. That's a lot of for loops, right? I'm not gonna do that. I'm gonna use TidyModels, right? Okay, I want to use the fit resamples command. Okay, fit resamples. So, how does that work? I'm gonna create a object who's gonna call cross-validation, could be any name. That please take my workflow, right? The workflow that we just defined. Take that workflow and do a fit resample where? In the folds that I just defined. Okay? So then it's gonna do this. It's gonna fit here, metrics, compute the metrics here. Fit here, take the average. Average accuracy, average whatever metrics we're doing. Okay? So here, how do I extract these metrics? I use collect metrics. Collect metrics. Here's the default. Notice is different than the default metrics are this. Not exactly as the other one, but okay, so these are the default metrics. And notice that since we have 5 folds, is the average of 5 accuracies, one for each fold. 5 Breer class and RC. Okay, so now I have my cross-validated metrics. That's actually like an estimation what I would have in the test set, but not using the test set. That's the trick. You're going to use this and not use the test. Now, okay, I did the logistic regression. I could have done another model, right? We've done it all out, and just parentheses. We did cross-validation. We could do bootstrapping. We could do another resampling methods. There's another bunch of them. Okay, so here, if you want to change the method. Okay, so we could try decision tree. Decision tree. Everybody knows a little bit about decision trees. They're split, right? Bifurcation. So, okay, I'm gonna define a decision tree, okay, using the parsnip, using the TidyModel. So, decision tree is decision tree. I have the 7 mode, remember, because decision tree has regression classification. I use the set engine, R part. This thing here is just because I want to get a plot later. If you don't specify, don't worry. And I'm fixing this. If I don't fix it, it's gonna have a default value. Why I chose 0.05? Because I want the picture to show
To fit in this slide.
That's why. Okay? Not more. Okay, so here, just coming back, I specified the model, so I called tree spec. The other one was log reg spec. Define the model. The recipe, I'm not even doing recipe separate because I'm just using the formula, so I can just include that in the workflow directly. The formula, virgula, comma, the model. Okay? This is my workflow. Workflow, I need to fit. Always the same. So define workflow, fit. I need, like for decision trees, like that we can have a plot. So you're not going to use the tide to get coefficients, you could, but to get some splits, right? But it's easier to have the plot. I have to do this part here. Fit engine to extract, and you can have a plot. Okay, so which one is better without using the test set? Cross-validation here again. So, okay, I'm going to use fit resamples again on the folds, but on top of which workflow? The tree workflow. So I just changed the workflow, right? And I collect metrics the same, and I get the cross-validated. So it's a little bit worse, right? Yeah. I could try, I'm gonna go fast now, so just you can compare. We could do random forest, you can go faster here. Okay, random forest, specify how many trees, if I don't, it's 500. Classification, the default is ranger, so I didn't specify the engine, the default was ranger, okay? You do the same, you get the workflow here, just the formula model. 50 samples, collect metrics. Now I can compare these tables and see, okay, I prefer random forest, I prefer based on this. I don't like to use accuracy, I'm going to use this. You just have to make a criteria and compare. Okay? Okay, let's say we decided. Okay, so here I'm doing one by one. We're not going to do one by one because we're going to try, I don't know how many. Remember, if you're not lazy, you're going to try a bunch of models. Okay, you're going to try a bunch of models. So then you can use what is called workflow set. So you make a set of workflows. How are you going to do this? You have workflow set function. You have 2 arguments. A list of pre-processing, a list of models. If I use cross-false, I'm just doing this with this, this with this, this with this. If I use cross-true, I can cross-product. So it's up to you. What do you mean? Then it has a workflow set. So I'm just saying, I have this many workflows, I need to fit them. I'm gonna use again fit resamples, but inside of this other function called workflow map, which is gonna get then your workflow set, workflow map. What are you gonna do with the workflow map? I wanna do the cross-validation thing, right? So fit resamples. So that's here. What and already can ask for ranking results. It's gonna say, okay, recipe one, this workflow, each one is a workflow. And it gives you the metrics. So that's easier. You can have a bunch of workflows here, and this line you get all the metrics, all the cross-validated metrics. Okay, so it's fast.
And go back, Samara. That is interesting because they have the same mean accuracy, but the standard error of random forest is smaller, so that's why it's ranked first.
Yeah,
Because it's very precise. Yeah.
yeah, it has like almost a tie.
Yeah.
Here, if you want to do the cross product, it's the same thing. Okay. So okay, let's say I chose, looking at these tables, logistic regression it is, right? I need to fit that, right? So then I use, now that I decided, I use the cross-validation matrix. Now, I'm gonna go with the test set and see. Now that's over. It's over. Logistic regression won, right? Now I'm gonna go train, because right now, like I was training just in the folds, right? Now I'm gonna go back and train and everything and test. I can use last fit with, remember the first split we did and training and tested? What this last fit does is, okay, train in the training, and when I ask collect metrics, it's gonna already give me on the test set. So this is from the test set already. So in the test set, it's 62. That's what we had before, right?
64.
Yeah.
But it's,
Yeah, for the cross validation was 64. So, yeah. But it was not 69. See how the cross validation is close to the test without using the test, right?
yeah, that's when we say that the model is very optimistic.
Yeah,
Train
always
set.
train. Yeah, always the train is gonna be higher. This
But you have
the other way around. There's something more going on. Okay, so this was the final model. Guys, you have time for a little bit more?
A little bit more.
I go quick.
There's,
Maybe like 10 minutes.
Okay, go quick, go quick.
it's just
Because
the tuning part.
Yeah, the tuning part.
Do you want to practice, demonstrate the, you want to demonstrate the now?
No, just the slide.
No, it's just showing.
5 minutes?
Yeah.
5 minutes?
Yeah.
So,
So just get you one question. We did the logistic regression with the polynomial of degree 2 for age. Who said that was good? I chose the polynomial. Maybe I had like information. Oh, this is good. The parabol works. Parabolic quadratic form works. Maybe yes. Then I already want to set that thing. The decision tree. I chose the cost complexity 5.05. Why? Right? Is there a way I can have a data-driven approach to choose those things? Right? I can choose between many different workflows that have this kind of decision that I need to do. That's called tuning. Tuning hyperparameters, tuning models. Right? We also can do here. Okay? So here, right, we had the degree 2, and the tuning may happen in 2 parts, just in the recipe, in the model, or both, right? So here I'm gonna show the first part is like, I want to tune this degree 2, why 2, not 3? I can test. But do I need to make a recipe? Recipe for degree 2, recipe for degree 3, no, I don't have to do that. I can use before.
Oh, no.
I will do. What I'm gonna do is, I'm not gonna set up a recipe for each degree of the polynomial. I'm gonna say, okay, 2. Leave it open, because later I have another function that's gonna do that. Right? So this is one thing. Right? So then I have the workflow with this recipe, with the tune. Instead of doing fit resamples, I'm gonna use tune grid. Tune grid again, because I want to use cross-validation again. So now it's going to do the cross-validation for degree 1, for degree 2, for degree 3. Everything it does for you. Which degrees? I need to give a grid of options. I can give the degree 1 to 6 for this thing, right? Up to 6, I can go there. Because it doesn't cost me anything to check. It's automatic. Right, so then I do collect metrics, and it's gonna say, okay, when I tested degree 1, degree 2, degree 1, those are the metrics. Choose the best one. Look at this. Okay. Degree of the polynomial. First degree for h, quadratic, 3, up to 6. Right? And then you see, okay, the best is kind of here. First degree is enough, right? You can do a plot. You say, okay, just show me the best. With show best, you need to specify the metric. Okay, you always need to specify. And you say, show me the best 3, or the best 1, and just n equals 1. Okay? So, 2 and 1 is like a tie. Right? Random forest, I can tune for the number of predictors I'm going to sample at each split. I can do that too. Okay? So I'm not going to do a tuning in the recipe. I'm going to do a tuning inside of the model. Inside of the model, okay, I define the model. This here, instead of leaving the default, which is the square root of the number of columns, I can ask tune that. Maybe you can find another better. And you just want to do the same, okay? Tune grid. Here, I didn't specify M3 data from values. To do this, say try 15 values. It's gonna try. It has algorithm inside that tries some values here, so you don't need to really specify. So try 15 values, try 20 values, okay? So that's another way to specify the grid. Collect metrics, you can have plots, showing the accuracy.
Different numbers of M try. See, there is 16,
yeah.
5, 13.
T try 5, 13, 16.
Yeah.
T try.
Random sample.
At each split, I tried 16 predictors to do the random forest, or I tried 5, or I tried. Okay, then show the best 3.
So I want to show the best. Can it, if you show the best, the command is show the best 5.
Yeah.
The total number is 5.
Yes.
You're going to group them in the best. The first
Yeah,
best.
gonna order. Yeah.
That order.
Yeah, gonna order. I can just get the first one. I can go with the. It's gonna or the same order. Okay. Okay, if let's say then, okay, random forest is gonna be my choice. Do I need to look at the table and see, oh, any trial of 5 was the best, or what? No, I don't need to do that. I just do select best. I don't even need to look at the results. I can do select best, right? Select best. And it's gonna save that best M try. And then I do finalize the workflow with that best one. And then I do last fit. Okay? So you can really automate this. Like And then so that was it, right? And then you can do a structured flow to go, what are the steps to get to the analysis, to this module, predictions. You can do, for random forest, we usually do this plot, right? Or the variable importance plot.
This is nice.
Right? You see how, like, what's the most
Important
importance. Yes. Right? But then in the website, I left another extra, that is, if you want to try many tuning models all the same time, this is the last portion of the material, you can really automate an easy bunch of options, okay? Okay, I think we're done. Tuning.
Thank you. Thank you so much. I appreciate it. The slides.
Oh, yeah, yeah.
The slides.
Yeah, you're interested.
Okay. And